and we shall start recording. So please, Richard, make some comments to the slides, please.
I was still silenced. Okay. Yeah, so you can hear me now, right?
Yes, please.
Good. Yeah, so thank you very much for giving me the opportunity to give a talk again in this seminar series, and I'm going to talk about enumeration of autocatalytic subsystems in large chemical reaction networks. And this is a joint work with Thomas Gatter, Peter Stadler, and Nicola Vassena, and I'm a PhD student in the bioinf group at Leipzig University. And to give you a small overview of what I'm going to talk about. So first of all, I'm giving a slight introduction to what is autocatalysis in general. And then I'm going to talk about two representations of autocatalysis, which are autocatalytic matrices, and then how these matrices can be translated into the directed bipartite Koenig graph representation. And the Koenig graph is also known as the metabolite reaction graphs in other fields, or the species reaction graphs. And if we have time, I think I'm going to show you also that we applied this framework to metabolic networks and what we can see in different kinds of metabolic networks. So first of all, what is autocatalysis? So autocatalysis is, as Alex Blockhaus in 2020 has framed it in his paper, the process by which a combination of reactions involves a set of species which all increase in numbers. And that means we have a set of reactions, we had a set of species, and we apply the reactions a couple of amount of times, not the same amount of times, but we get a net increase for all the species. And it has been shown that autocatalysis is important, not only as a theoretical framework, but also in real life. And this was shown to be relevant for the origin of life, which has been substantiated also by the discovery of the Fomalhaut reaction. But it was repeatedly claimed that it is actually rare in non-enzymatic chemistry, but abundant in metabolic networks. And the question was, can we basically find a mathematical framework in order to make the enumeration of autocatalytic subnetworks feasible, so that system biologists or system chemists can use a tool in order to analyze their networks they like the most. And when we have,
Excuse me, Richard, if I take the reaction X goes to Y, then Y will increase. Is there any autocatalysis here? I don't think so.
No, an X goes to Y, no. But it
corresponds to the definition, in the first line.
No, but we have to have that all of the species which are involved increase in number. So also the X has to increase in this case.
All of the species. Here, a combination of reactions involves a set of species, a set of all the species.
Yes, then but X is also a species, isn't it?
Yes, but then you should here write a set of all the species.
Well,
so I think it is a subset.
It is a subset. Yes. So basically, I mean, this is not my definition, but yes, this might be can be given more specific, but you may not choose all of the species. So for example, in an autocatalytic cycle where you have, I don't know, X goes to Y and then Y goes back to 2X, but you have also some kind of other food which is involved, and waste molecules, then the food will not increase. But the species you're selecting for will increase, and this might become more clearly when I'm going to talk about it later.
Okay, let's go on.
Okay. So when we have, for example, look at the glycolysis, then the glycolysis is basically an example for autocatalysis because we put 2 ATP molecules inside the glycolysis and we get 4 ATP molecules out. But here we have to, as I said, what we have to take into account is that we always assume that there is a sufficient amount of food molecules which are present in order to make this process running. So this is not like a perpetuum mobile. And maybe some preliminaries I want to introduce, because the chemical reaction network, as I think about it, is maybe a little bit, not completely, but a little bit, or the representations are a little bit different what you usually think of. So for example, we think of a chemical reaction network as a set of species and a set of reactions, such that we can write all of the reactions or for all of the reactions, we can write a stoichiometric equation in the way I've shown it here in this first equation, and then we can arrange the stoichiometric coefficients in a stoichiometric matrix. And here the net stoichiometries. This gives us one representation of the chemical reaction network, but we also can find another representation which is very important for us in this talk, and this is the directed bipartite Königsgraph or metabolite to reaction graph, which is composed of two disjoint sets of vertices. So we have metabolite vertices and we have reaction vertices. So the metabolite vertices are here depicted as circles, and we have the reaction vertices which are depicted as squares. And we have two kinds of edges. So the metabolite to reaction edges, and we have an edge from a metabolite to a reaction whenever this is a reactant for this reaction, and we have the product edges, and we always have an edge from a reaction node into a metabolite node whenever this metabolite is a product of a reaction. And this is basically the overview of the talk. So a little bit the roadmap of what I want to talk about. So what we want to do, or what we have also shown in the paper, is that we're not looking for all the autocatalytic matrices, because this would be computational infeasible, but we're looking for a specific subset of autocatalytic matrices. And these are the autocatalytic child selection matrices with irreducible Metzler part. And I'm going to say what all of those concepts mean. So what is the child selection matrix and what means irreducible Metzler part? The problem is, like in a graph representation, the stoichiometry is not encoded. And this is why we cannot find a direct representation of these matrices. We can only find a representation of child selection matrices with irreducible Metzler part. And after we extracted basically the graph representation and then the matrix, then we can basically check if this matrix is autocatalytic. And the equivalent graph representation are so-called fluffles. And fluffles are strong blocks with particular properties, so that the number of reaction vertices are identical, and every species vertex has out degree 1, and every reaction vertex has in degree 1. And then our goal is basically to enumerate these fluffles in an efficient way. And we can do so by taking advantage of elementary circuits and basically superimposing elementary circuits, so sticking elementary circuits together, and getting subsets of the power set of all elementary circuits, which are circuit nets. And then we can find those circuit nets that give us, or that yield a fluffle efficiently by using an equivalence relationship. And this is a child selection equivalence relationship, which is defined basically on the reactant to reaction edges. And I'm going to explain this in more detail later on. But this is what I want to do in this talk. Okay, and before I start with the definition of an autocatalytic matrix and how we see it here, I just want to say that I'm not going to include in this talk explicit catalysis. So an explicit catalytic reaction is whenever a species appears as both as a reactant and as a product in one reaction. And when we have a look at these two reactions here, we see that they both share the same stoichiometric matrix. But that means that the stoichiometric matrix not anymore uniquely identifies as the reaction network. And for this work, we're excluding any explicit catalysis. And because we've done this in another paper, which is called, which you can find here. This is autocatalytic cores in reaction networks with explicit catalysis. And what I also will not discuss here is another framework which relates to autocatalysis, and these are the so-called reflexively autocatalytic F-generated sets, which were, I think, the first time introduced by Wim Hordijk and Mike Steele in 2004. This is currently ongoing work in our research group to find the overlaps between these two kind of notions. Okay, and with this, we can start with the definition of an autocatalytic matrix. And an autocatalytic matrix is a submatrix of the stoichiometric matrix, such that two things are satisfied. So first of all, we want for each reaction, so in each column, a positive and a negative entry, which means that we have a reactant and a product for each reaction. And we want to have a positive or a vector, a strictly positive vector of reaction rates, such that if we multiply it from the right-hand side to our matrix, we get a strictly net increase for each of the species. So we get a positive vector as a result. And this might be more easily seen at an example. So for example, if we have x2 going to 2x1 and x1 going to x2, and we get this stoichiometric matrix here, and then with this strictly positive vector, we obtain a vector which is strictly positive when we multiply this vector v to the right-hand side of S. So this is an autocatalytic matrix. And then relatively quickly comes the question, okay, is this the smallest autocatalytic matrix I can find when I consider these kind of species and reactions? And this leads to the definition of an autocatalytic core. And an autocatalytic core is nothing more than an autocatalytic matrix that does not contain any proper autocatalytic submatrix. And the example before is or was an autocatalytic core, because I cannot find any autocatalytic submatrix inside here anymore that satisfies both of the properties I've said, because the single positive entries would not satisfy that I have a negative and a positive entry in each of the columns. So this here is an autocatalytic core. And then in the paper from Alex Blockhaus in 2020, they characterized the autocatalytic cores into 5 types, which are those 5 types, and they proved that these are the only 5 types that can occur. And this was in a setting where all the reactions were considered reversible. So I know, of course, this is in general or in theory the case, but in biochemistry, sometimes the activation energy is so high that some reactions are considered actually irreversible. And this is why we consider here a more general case and where the reactions can be reversible and irreversible. So there can be also different types of cores than the 5 identified here. And autocatalytic cores has been shown that they satisfy some interesting properties. So these are square and irreducible and invertible matrices. And one more very important thing is that for these cores, there exists a reordering of the columns such that we obtain a matrix with a strictly negative diagonal and a non-negative off-diagonal matrix. And such matrices are called Metzler matrices. So Metzler matrix in general is called when it's a non-negative matrix on the off-diagonals, but in our setting, we will always, so when we exclude explicit catalysis, what we do here, we will always end up with this strictly negative diagonal. So back to the example from before, When we switch just these two columns here, then we obtain a matrix which is a Metzler matrix. And one other thing that can be seen from this Metzler representation is another property of an autocatalytic core. And this property is that every reactant is, or every metabolite is a reactant for one reaction and one reaction only. And each of the reactions has one reactant, just one. And this can be now made formal by the concept of child selections. And the child selection is formally a triple. It's a subset of the species and a subset of the reactions, which are of identical size, so of size k here. And we have a bijection from the subset of the species into the subset of the reactions, such that each metabolite chooses its reaction for which it is a reactant for. So that means that the stoichiometric eta coefficient of the species and the image under the bijection is strictly positive. And then we can call, or we call this bijection also a child selection bijection. And this is maybe also more impressive or more understandable at an example. So for example, in this graph here on the right-hand side, we only have, or this graph, we can only have one child selection. So A chooses R1, B chooses basically here R2, and C chooses R3. And this is also, by the way, it's an autocatalytic Metzler matrix. It's also an autocatalytic core. In general, there might be multiple child selections. In cores, there is only one child selection possible. And then I said that we're going to look for matrices with irreducible Metzler part. And the question is, so why irreducible matrices in general? So when we have a reducible child selection matrix, then we can represent this matrix in a block form that comes, or that originates from a cascade of irreducible child selection matrices. And when this matrix is also Metzler and autocatalytic, then we can find a subchild selection of the original child selection, such that the subchild selection matrix here in the in the upper left triangle is an irreducible autocatalytic Metzler matrix, child selection matrix. Okay. And to sum this up, so we excluding here in this, so in to sum up the first part here, we're excluding explicit catalysis, and this is why our stoichiometric matrix uniquely identifies us the chemical reaction network, and our 8 autocatalytic matrices uniquely identifies as the autocatalytic subsystems in this network. And autocatalytic cores are inclusion minimal autocatalytic matrices, which are irreducible and which have a representation as a Metzler matrix, which is also a child selection matrix. So autocatalytic cores satisfy all the properties we were at the beginning looking for, because we set out at the beginning to find all irreducible autocatalytic Metzler child selection matrices. It turned out that we find all autocatalytic child selection matrices with irreducible Metzler part. So the question is, what is a Metzler part? So when you have a child selection matrix, which is a non-Metzler matrix, so that has a negative off-diagonal entry, you just basically turn these off-diagonal negative entries into zeros. This is what we then call the Metzler part of this child selection matrix. And this Metzler part of the child selection matrix has a specific representation in the Königs graph, which is what I'm going to show next. So now what we want to do is that we want to translate all of the notions on the matrices into a graph representation. and what that means for the directed bipartite Königs graph. And maybe I start with the child selection, and we can have a look at this from two different perspectives. So we can take a subgraph of the Königs graph and ask, is this graph child selective? That means, does there exist a map from the subset of the species into the subset of the reactions, such that I can find, such that this map is bijective and that this is also a child selection. And of these examples I've drawn here, the first one, yes, this is child selective. These are two elementary circuits which are not connected. So elementary circuits are in general child selective, and of course, if they're not connected, then their union is also a child selection. It's also child selective. But from B to F, or from B to C, D to E, what we violate here is that we require that we have the same amount of species vertices and we have the same amount of the same amount of the reaction vertices. And this is violated here from B to E. This is why these graphs B, C, D, and E, they are not child selective. And in the graph F, I have basically for X1, I have two possibilities. I can choose R2 or R3, but for X3 and X2, there's only one choice, which is R1, so that we cannot find a child selection. And then the only one which is left here is the graph G, and this is what we've already seen. We know already that this is an autocatalytic core, so this one is child selective. And then we can find a nice graph characterization for child selectiveness, and this is basically that the subgraph is child selective if and only if the subset of the reactant to reaction edges contains a perfect matching. And yeah, here I've shown a graph which has two perfect matchings, the blue one and the green one. And it is indeed also the case that you find that there's a one-to-one correspondence between perfect matchings and child selections. We can also have the other perspective on the graph. So we can also have the perspective that given a child selection, what kind of subgraphs do we find? And we have two kind of induced subgraphs that we can define here. We have the vertex-induced subgraph. So this is induced by the subset of the species and the subset of the reactions. And if we take this child selection with this child selection matrix, this is basically the vertex-induced subgraph we can identify, we end up with, and we find now, and this is why I marked this here, this off-diagonal entry that gives us an additional species to reaction edge. But we can also have a look at the child selection induced subgraph. And the child selection induced subgraph has only those reactant to reaction edges that are defined by the perfect matching or by the child selection. And this is when the negative off-diagonal entry here disappears, or when we do not have anymore this additional species to reaction edge. And then the Metzler part of this matrix gives us basically this child selection induced subgraph. And this is what I said at the beginning, or at this one slide, that the Metzler part of the child selection matrix has a specific graph representation. And we can observe that in the child selection induced subgraph, each of the species has out degree 1 and each of the reaction vertices has in degree 1. And the other way around, it is also true. So when I have a subgraph such that the number of the species vertices is identical to the number of reaction vertices, and every species has out degree 1 and every reaction vertex has in degree 1, then K prime, then on my subgraph is child selective. Okay. And then the question is, what does the irreducibility basically of the matrix imply, or does the irreducibility of the Metzler part implies? And in general, when I have a digraph that is strongly connected, then, or a digraph is strongly connected if and only if its adjacency matrix is irreducible. So this is something which is known. And the question was for us, okay, could we find something, some kind of notion also for our child selection matrices? And when we have a look at this child selection matrix, the additional off-diagonal negative entry gives us basically two possibilities to go to X3. If we remove that entry, then there is only one possibility to go from X1 to X3. This is the idea also how the proofs works. And then the Metzler part of my child selection matrix represents as a transpose the adjacency matrix of the associated metabolite graph. And then we get the result that if I have a child selection, then my child selection induced subgraph is not only strongly connected, but even more, it is a strong block. That means it is also that the underlying graph is also too connected if and only if the Metzler part of my child selection matrix is irreducible. And all of this together, all of these things that we translated now into the bipartite Königs representation gives the notion of a fluffle. And so that means if I have a subgraph G of my Königs graph, and there is a child selection with a child selection matrix that has an irreducible Metzler part, such that G is actually the child selection induced subgraph. And this is the case if and only if G satisfies what we've shown, that the number of metabolite vertices is identical to the number of reaction vertices. Each of the metabolite vertices has out degree 1, and each of the reaction vertices is in degree 1. And G is basically a strong block. And the question is, so what kind of matrices are fluffles? And this is these graphs we call fluffles. So elementary circuits are, for example, fluffles. What we've already seen, this more complicated structure is a fluffle. But whenever we violate, for example, the condition 1 here, then of course we will not end up with a fluffle. Okay, so we now have found a representation of the graph for the child selection matrices with irreducible Metzler part as a graph. And the question is now, how can we obtain these graphs efficiently? And for this, we might need another idea on how to do that. And strong blocks are exactly those graphs that have an open ear decomposition. Or in another way, a graph is a strong block if and only if it has a directed open ear decomposition. And what does an open ear decomposition mean? So if I have my strong block, then I can basically take off here such an ear. And an ear starts in some vertex, it ends in some vertex. All of these vertices, they have in degree 1 and out degree 1. And I can find a path back from my terminating node into my starting node. And in our case, for the fluffles, this ear decomposition has a specific structure because the ear can only start in a reaction vertex and end in a metabolite vertex. Yeah. And then the question is, okay, can we reverse this process? Because we know that elementary circuits are fluffles. So can we somehow reverse this process and elementary circuits can be enumerated somehow efficiently? Can we reverse this process by using elementary circuits and sticking them together in a way that we end up with a fluffle in the end again? And yes, this is possible. So in this case, if I have a fluffle, if I start with a fluffle and I add an elementary circuit to that fluffle, then I get a fluffle back if and only if each of the connected components of the intersection is a path that starts in a metabolite and ends in a reaction vertex. So basically the example from before, we have the two elementary circuits, we know these are fluffles, and they share this path from a metabolite vertex to a reaction vertex from A to R1. And if I stick them together, then I get basically my fluffle back. And this can get, of course, arbitrarily complicated. So I can add also another elementary circuit here, which shares this path C1, C2R3. And these paths, they do not have to be, as I said, each of the connected components of the intersection has to be such a path. So here, for example, the green and the blue elementary circuits, they have two connected components of the intersection. So A to R1 and D to R4. Okay, and this means that fluffles can be composed by suitable superimpositions of elementary circuits. And then the question is, but does every fluffle can be composed in such a way? And indeed, this is also true. So for each fluffle, there exists a set of elementary circuits, and we call these sets of elementary circuits so-called circuit nets, such that their union gives us the fluffle. Good. But the problem is that many circuit nets induce the same fluffle. So for example, the circuit net 1 here, which is composed of the elementary circuits C1, C2, and C3, so the green one, the blue one, and the red one, they induce the same fluffle as the circuit net C, as a MAFCA C2 here, which is composed of the elementary circuits C4 and C5, which have both the same also child selection matrix. And then the idea was, okay, could we define just a fluffle equivalence class, which is based on all of the edges in the graph, and we say that two circuit nets are identical or equivalent when the union or the edge set of the union is the same. And this reduces already the number of circuit nets that have to be enumerated. But actually, we did not set out to enumerate fluffles. We actually set out to enumerate child selection matrices. And whenever you have the E1 edges, so the reactant to reaction edges, so the diagonal entries of our child selection matrix, we already know about the rest. So the rest of the graph is basically just the induced subgraph, and we already know all the other entries. And this led us to introducing the notion of a child selection equivalence. And this child selection equivalence is defined on the reactant to reaction edges. That means that two circuit nets are identical if the union of the elementary circuits have the same E1 edges. And then, yeah, we get basically, as I said, we get back all the other entries. And in this example, 28 out of 31 circuit nets belong to the same equivalence class. I mean, this is a special example because this is a type 5 autocatalytic course, which has not been observed right now yet in metabolic networks. But I'm going to show later that the number of child selection equivalence classes we had to enumerate was dramatically reduced in contrast to the fluffle equivalence classes. And then the last question was basically, so if we have one circuit, a representative of one equivalence class, and we take an elementary circuit of one of the equivalence classes of the child selection equivalence class for the elementary circuits, do we get basically the same as if we take two other representatives of each of the equivalence classes? And this is also true. Maybe this example is not the best one because C4 is already inducing the whole graph. but C4 and C3 gives the same, as well as C5 and C3. That gives us also the same graph. Okay, and with this, we could dramatically reduce the computational complexity of the stuff we had to enumerate, not for the elementary circuits. So for the elementary circuits, the number of elementary circuits and the number of equivalence classes were practically identical. And the only case when this is, the only case when this is not identical is when one have basically some kind of type 5 autocatalytic core, because then there are two spanning elementary circuits, and then just one is enough. But if one compares how many Fluffel equivalence classes in contrast to child selection equivalence classes had to be enumerated, then there is a clear difference. And this made this notion of child selection equivalence class made in the end it possible to enumerate also autocatalytic subsystems of larger sizes, so beyond elementary circuits. And then we applied this to different kinds of networks. So to the E. coli network, for example, to the E. coli core metabolism, for which we could enumerate all autocatalytic child selection matrices with irreducible Metzler part, and also to the human erythrocyte network, which was in a big database. But here we had to basically stop at 25 metabolites. And maybe what one can see is also for the, maybe I go a little bit closer, that we can find, for example, cores. So if I can find autocatalytic cores also for sizes of 24 and 25. And we have seen now also in another paper already very large cores, autocatalytic cores. Okay. And yeah. Well, sorry. Let's see. But there's one thing that is still or was still a problem. So if you're interested only in the enumeration of autocatalytic cores, then the problem is that the number of elementary circuits, they dramatically increase, and in some networks and some graphs, they grow super exponentially. And the question was, could we do something about this? Because we now know about the structure of the of autocatalytic cores. They are represented as fluffles. So can we do something about this that we don't have to enumerate actually all the elementary circuits? So because if we know if there is a metabolite to reaction chord in the elementary circuit, which induces a negative off-diagonal entry in the child selection matrix, then I will always have this chord. Whenever I stick this together with other elementary circuits, this negative off-diagonal entry will remain. And then we came up with the idea of enumerating only EMMA chordless elementary circuits. It means all those elementary circuits that do not have metabolite to reaction chords. So no shortcuts from metabolite to reactions, only shortcuts from reaction to metabolites within the elementary circuit. And on all the metabolite to reaction edges were located along the elementary circuits. And with this, it was actually possible to reduce the number of circuits that had to be enumerated in order to find even larger sizes of autocatalytic cores, and also in larger networks. And I've shown here some of the results that are from our paper, or from our preprint. It's still a preprint of autogatito, as we call this other, or this smaller tool. And here you can see that we actually, for Helicobacter pylori, we were able to enumerate all the autocatalytic cores from the Helicobacter pylori network. Yeah, and to sum this up, we have found a representation of child selection matrices with irreducible Metzler part as fluffles, as I've shown you. in the directed bipartite Königs graph. And we have shown, or we found also an efficient way, or a way to enumerate these fluffles via child selection equivalence classes, or to reduce the computational complexity for enumerating the circuit nets that we need to find our fluffles via child selection equivalence classes. And we've implemented this as a software, which is called AutoGatto, which is available on my GitHub page. And at the end, I've shown you that we were also able to refine this algorithm by not enumerating all the elementary circuits, but only the ones without metabolite to reaction cords. And the tool is called autogatito, but it is still under the repository of Emma codeless circuits. And I will, because this is for the revision process, if this is done, then I'm going to include it into autogatto. As I said at the beginning, this talk was not about including explicit catalysis. So we excluded explicit catalysis within this talk, but we've now also extended this framework to reaction networks with explicit catalysis, which is another paper. And currently we are working on a C++ implementation of autogatito in order to apply it to larger metabolic networks, because the problem right now is a little bit that in Python, the parallelization, especially for the Linux system, requires that, so to have a real parallelization requires that large data structures have to be copied. And this is then can get people to run into memory issues, which also happened to us, so we had to be a little bit careful. And as I said also at the beginning, we currently compare the framework that comes from the definition of Alex Blockhaus now with the RAF framework, so with the reflexively autocatalytic F-generated autocatalytic networks, and trying to find what kind of conditions induce basically in the RAF framework autocatalytic cores, and also the other way around. So how these two really different definitions go together. And we're still also working to apply our framework to different kinds of chemical reaction networks. So we're working currently also together with some people who are having carbon fixation or networks with on carbon fixation, and we also want to apply our tools there. Okay, and with this, I want to thank especially these three people, so Nicola, Thomas, and Peter, but also all the people from the BioInf group, the German Network for Bioinformatics, because they bioinformatics infrastructure, because they provided us with additional computational resources. The SEC AI, of which I'm an associate member, for travel funding, and also the Metomic project and the Novo Nordisk funding for funding the Metomic project, basically. Yeah, and I thank you also for your attention. And if you have any questions, hopefully I can answer them.
Thank you very much. And